Okay. Hello again. Hello, everyone. Thanks for coming again. Um, so the very basic obvious stuff, as usual, just please interrupt me whenever you want. Also for the online participants, just open up the microphone and ask something because, chats are just hard to follow. And our video just tend to be blurry. So if it is blurry, just again tell us. And so that's it. Neil also asked something about the references, right? So you all know, I hope, that there is a page for the course, and then the address is you can find it on my own webpage, or also it is just in the announcement that you had. And there are some references there, the link to the YouTube, Opera, whatever. And but just to be, very concise about it, now we are doing category theory. My main reference is either the category theory book by Steve Audi, and also the draft of my own book, just to promote myself. Okay, so now we can start with a quick recap, right? So last time we had limits and co-limits, right? So we had that we had category C, and then we talked about the limit, and so you have a diagram, say some nodes. These are just objects in C, say A, B, C, whatever, and then you have some maps, right? So some diagram could be finite, big, but small, in the sense that everything just is a set. And then the limit of this guy is just one object and morphisms to each of these guys such that everything commutes, right? So it's cone. This is a cone, and the best cone, the greatest possible cone is the limit. We saw that, meaning that you have a cone and any other cone, right, factors uniquely through our biggest cone. And then dually, if you have just, you can have co-cones, right? From the diagram, you go somewhere, and then that's the least, meaning that, whatever co-cone you have, you can just factor it uniquely. So limit. Yes. So what's a cone? A cone is obvious, right? So this is the greatest cone in the sense that this is a cone, one, two. For any other cone, there exists a unique map from the heads of the cones such that everything commutes, right? So it really, so what I'm saying is that there is a map that each of these edges are factored through that one, right? And the guy is unique in that property. So we had some examples, so many of them actually, right? So of course. In general, this relation map is not the objective. Just the map. Yes, sure.
So this existence of uniqueness, can it be like philosophically split down and like why existence and why uniqueness, or is this just because like this limit being the biggest one makes sense in some, but it's a little bit unintuitive. Why should I think of the existence of a unique arrow as a something to compare, but if there are two arrows, I ignore it or something like
Yes, I see your point. How to motivate that? Apart from using the representability and the usual stuff, if I want to do it just in normal language. So if you want, you need some sort of universality, right? The biggest in some sense. And that being biggest, when you have morphisms, it means that there are different ways to be the big, right?
Actually, I don't understand what you mean.
Just very informally, the biggest. Meaning that, okay, so for instance, this guy is something above all of these guys, or below. It depends on how you interpret it, right? That doesn't matter. So let's say that you have something and this guy is above this. But then the biggest means that for any other thing above, so this is the lowest possible. Okay. Okay, change it. So uh, this is less than the diagram. And then the biggest of the lower bounds is what I mean by the biggest, really, right? Meaning that it is a lower bound of all of them. And for any other lower bound, right, that you find, that lower bound is less than our greatest lower bound, right? So in this sense, it is the greatest with some property. The property is lower bound.
We should think that these arrows actually, in some sense, indicate the position itself.
Kind of, yes. Right. And then the question is that, okay, if it is the picture, then the greatest should be just the lowest in this picture, right? And then why I'm insisting on uniqueness. And the point is that, okay, when you have just different morphisms, there are different ways to be, sit inside another thing, right? So I want this guy to be unique uh, to really, to have just universality in this. Okay, I don't know how to say it. Okay, maybe one motivation could be this. If I erase this uniqueness condition, then the guy could not be unique, really. So you assume that the guy, whatever it is, it should be unique up to isomorphism. And this heavily uses the uniqueness. Right? So but in some sense, you have just objects and morphisms, right? So you have to care both of them, not just one. So, right?
So can I think of this uniqueness as the object not being ad hoc in some way, and this is the biggest non-ad hoc object?
You have to think of it as some sort of the biggest in canonical way, right? It is, it's really the biggest, uniquely determined in some sense.
I have this biggest one in the unique way, and I would just imagine one a little bit up before it, and I add two arrows. Can I see like what breaks? Is there some kind of non-commutativity happening? Or
It depends on the thing. So um, you need some specific example then, right? So let's say that our specific example is just a product, right? So if I have products, then I have this A times B, right? And then you are saying that, okay, so maybe I can explain here what everything means, right? So first, these two arrows simply mean that everything here is a pair. But it does not say that all the information is recorded in the pairs, right? Then you say that it is the biggest, meaning that for any other thing, right? You have a map.
So you could put the 0.
Yes.
That would be a
Here you mean?
bad.
Yes.
That would be a bad.
That would be the bad code.
That should be unique. Because
Okay, so let's say that you have. Okay, let me complete what I was trying to say, and then I come back to that, right? So what was I wa okay? So I wanted to explain the thing. First, you have this cone, meaning that everything is a pair. Then I was saying that for any two morphisms, there is a map here, not uniqueness, just one map, meaning that I can pair any two elements to one element, right? So these two together means that everything is a pair and nothing else. But it does not say that a pair is uniquely determined by the two parts, right? So that uniqueness says that you can just really separate it into two parts of the information, right? So it says that you have AB right here, and you can break it to A and B in a unique way, right? So for instance, I can have the same information if I put some sort of, say, quotient here, right? Then I have the same data, right? Roughly, but you see the thing, right? This is one thing. The other is that, okay, let's say that we play with one, right? Then you are picking two elements, A and B, and then we expect to have a unique thing, right? What is the map? The map just picks some guy here, right, in A times B, such that the first element is A, the second part is B, right? So it simply says that there is unique pair with A in the first coordinate and B in the second coordinate, right?
So, but that's not, you needed a more general uniqueness condition.
Yes.
So one might think that that's enough for it to behave like just not
In set, yes. Simply because you can understand the object A by the maps from 1 to A, but we saw that this is not the case, so you need more things, right? Okay, so we had the limits. We had many examples of limits, right? So you remember that. So if you have just empty diagram, the limit was 1, the terminal object, and the initial was 0. Terminal means that there is one map from anything to the guy, a unique map to all here. And we had, so if this is your diagram, then we had the product of these two, the limit is the product. And so if you have the same thing, the co-product is just the co-limit of the diagram. So in set, this is just the product. This guy is just a disjunction. These are projections, these are injections. And then we had this kind of diagram. So the co-limit of this guy is just a co-equalizer, right? It simply means that just do the quotient to make these two equal. And the limit of this is just find the part here that these two are equal. And then we had also this diagram. So the limit is pullback, just fill the corner in the greatest possible way. And we also had push out. So fill this corner in the least possible way, right? And also remember that in the pullback, so the intuition was that it is kind of the inverse image, right? So if it is just monic, meaning that it sits here, this is the inverse image, right? Okay. So these were, say, the limits, co-limits that we saw. All of them are unique of isomorphism, and there we use that uniqueness. And that's it, right? So we computed them kind of in some of the categories that we had. And now I want to just complete the things that I said with what? With one observation, say, is it right? Yes. One observation about pullbacks, and then one pullback lemma, right? That I want to use. So the first observation is that I said that pullback is just the abstract version of inverse image, right? So I have to justify it in the following sense. That, so observation 1, so if you have some monic map, right? And then some another map, therefore we said that if we have the pullback, and we don't have necessarily the pullback, but let's say that we have the pullback, then this guy is the inverse image of that guy over this F, right? That was the intuition. So if it is correct, then this guy should be also a monic. The pullback of a monic should be a monic, right? Is it the case? Yes. How do I know that? That's a good so that this guy is a monic, say, and these. So I want to show that this guy is a monic. So I have two morphisms, the composition are equal. I have to prove that these two are equal, right? How to prove that? The only information that I have is that this guy is unique and this guy is a pullback. Exactly. So first you have the commutativity. These two are equal. Therefore, these two are equal. And this guy is Monique. So then the composition of these two with this guy are equal. So actually there is one map then here, not two. And now I have, so let's say that the composition of these two with this guy, which is just one morphism, is this guy. So I have just a corner, right? And the corner should be factored just in a unique way. So then these two guys are. So just, I want just to show that how to play with this thing again. So observation number one. Observation number two. Let's say that I have map from X, say, to Y, and here I have identity, right? What is the pullback? Identity again, right? Of course, it is commutative, but you can easily see that it is a pullback simply because if I find something here such that the composition with identity is just this guy, right? So then you can factor it just using the function here. You cannot do anything else. That's just easy. Intuitively, it means that identity is unique for obvious reasons, right? And it is a subset then of Y based on our interpretation. It's a sub-object of Y. It is just a total sub-object, right? The whole thing. So it simply says that the inverse image of the whole thing is the whole thing, right? So if you have some map and as a subset here, you have just the whole Y, then F minus 1 of Y is just the whole X. So that's the categorical version of that. Okay, so is there any other observation that I want to make? Maybe not. Okay, so then I need a limb, the pullback limb. The pullback lemma is just the following. So first, you say that, let's say that I have this. Right? That's a commutative diagram that I have. Of course, these are also important. Right? Two squares. Everything is commutative. So the first part says in the pullback lemma that if this guy is a pullback, this guy is a pullback, the whole thing is a pullback. And the second says that if the whole thing is a pullback and the right one is a pullback, then the left is a pullback. And the other one is not true. So it's antisymmetric. It is important that it's right, right? I don't need the second one, so just don't care about that. And you can prove it somehow with the other one if you have enough pullbacks. But the point is that I want to use this observation that if these two guys are pullbacks, then the whole thing is a pullback. And the proof is just kind of easy, right? So you can play with the guy like this, that put something here, you have to factor it. So you go here, then here, so you can come from this here and here. Then you can factor it like this, and then you can factor it. So this is just the existence. You can play with it to prove the uniqueness as well. So that's just easy.
Sorry, in the statement, you say that
If this is the pullback.
So what are the diagrams?
So
is there just one diagram like this L or?
what do you mean? These two guys are pullbacks, right?
Of what?
That's a good question. So there are two ways to say that something is a pullback. One way is this, that what is the pullback of this over that? It is this guy, and then you have this. The other way is that you can say that actually the square is a pullback square. right?
Okay.
So what I'm saying simply is that this is a pullback square, or equivalently, this guy is a pullback of this, or this guy is a pullback of that. The same here. And now over the big one, this is the pullback along this. Sorry, this is a pullback of this along this, right?
But the definition of pullback square is just at the top left thing.
Yes, of the rest. Exactly. So, okay, just easy. Intuitively, what I'm saying simply is that the composition of inverse images is the inverse image of a composition. So f minus 1 of g minus 1. And we saw that pullbacks are substitutions, if you remember, right? So I can remind you that, so let's say that I have just a map from x to y and some subset u. And then the pullback is what? It is f minus 1 of u sitting inside x, right? And then if you read this guy as a predicate u of y, right? F minus 1 of u of x, which is this predicate, the pullback, is simply u of f of x. Because something x is in f minus 1 of u if f of x is in u, by definition. So then you can, if you read this guy as a predicate, you can say that I have a predicate and I do the substitution to get another predicate, right? So pullback is substitution. And this says simply the composition of substitutions is a substitution. Okay. So there is another thing about pullback that we need. And that thing is always hard. Yes, thanks. And that thing is the following observation. So let's say that you have a map, F, right? And you have another map, and you do your pullback, okay? And also you have another map here. And you do the pullback of the other map. So think of two maps over this guy, then pulling back along F of the two would be this, and say this, right? So therefore, I have this pullback. So that's not very beautiful. Maybe like this. Okay? So, and then if you have a morphism here, then you have a triangle over some y, say. If you pull it back, this guy would be this, that guy would be this. Then the theorem says that you can fill here with one morphism such that it gets commutative. 1, 2, the guy is unique. 3, this guy above is a pullback, right? So filling in a unique way is just easy, simple, right? Because this guy, big one, is a pullback, right? This is why I have colors, right? So this guy is a pullback. And you want to find a map to the corner. The only thing that you have to do is just to find two maps to these guys such that everything gets commutative, right? So what are those maps? One is this, right? And the other is this. And then you can use just the commutative of everything to show that it is commutative. So you have this and it is unique. So how do I know that the above guy, this guy, is a pullback then? Yes, the pullback lemma, right? It's kind of hard to see that, right? But you have this and you have that, right? And just push them to make it flat, right? Then you can see it. So the big one is just this guy, right? The big one is a pullback, which is this blue one. And the right one is this guy, which is a pullback. Therefore, the left one is also a pullback. Am I right? Or it's the other way around? So anyway, you can use it. Yes. Yes. But I used. Sure.
But drawing these diagrams, so all the information's there.
Yes.
And you're waving at it and saying this is a pullback.
Yes.
So that's a statement about some point being minimal in some sense.
Yes.
Is there any notation for that in the diagram?
Yes. So to denote that the some square is a pullback, sometimes people write this, that this guy is a pullback, or PB, that is a pullback. I'm not sure if it helps, but
You should follow the arrows forward and then look at where those points join.
there is one corner. Of course, if I write, let's say, this, then that's kind of confusing, right? Because it could be this guy or the big one, but, you know, usually it means just a small one.
All right.
Okay. Sorry about this diagrammic game, but it is what it is. So, okay. So we had some pullbacks here or there, right? Some pullback games. And so what's the point of this guy, this lemma? It proves something obvious but interesting. And the interesting part is this. So first, the observation that we had that the pullback of a monic is a monic means that if I have a map from X to Y, then the pullback, let's write it like this, as operation, pullback along F, reads a subobject in Y. And then the lemma says that the pullback of it is just a subobject of X, right? Here I mean, by this F star, I mean that if you have F and say the monic U, and this is say G, this is F, by F star
Please focus the camera.
of G, it is blurry, I guess.
It is blurred, so please focus it.
We are trying. Okay, that's better. Thanks. So by this definition, I mean F star of G, G is the sub-object, meaning this. It is just this guy, right? So it is F star of G, whatever it is, right? So then, of course, pullback of a map is a map. But then if it is monic, then the answer is also monic, right? So simply, I'm saying that F star maps sub to sub, right? As a function, right?
So you're stating some kind of lemma that you wrote that says that if G
Yeah.
is money,
No, not these lemmas. This first observation, right?
G is money, then pullback of G is money.
Yes. So this guy is also monic.
Same.
Yes. Okay. So inverse image is just preserves the monics. So then this guy here. Yes. So let's say that I have a, yeah, this one. Yeah. It says that let's say that you have, let me draw the main part here. Let's say that you have two maps over some point, and this is your F, right? If you pull it back, pull this guy back, and pull this guy back, right? Let's say that you can do that. Then the lemma says that if there is a map here, it is possible to fill it with the map here in a unique way, such that everything, you know, becomes commutative, and then the above is pulled back, but I don't care about that, right? So you can read it as say the pullback of a triangle is a triangle, something of that sort, right? So the point is that you can use it here, really. So if I use this on this specific case, the result would be that f star is not just a function, it is also order preserving. So you remember that there is order on sub-objects, right? So we had, so a sub-object is a monique. So you have something. This is a monique, say, this is a sub-object, right? Say G. And there is another sub-object, say H. And there is order between them. The order is that if there is a map here, such that you have the commutativity, it means that U is less than V, right? Actually, G is less than H, right? So, therefore, sub-objects, it is actually a pre-order, right? There is some reflexive transitive order. So I'm saying that pullback just preserves the order, right? Why? Because if it is something, it is another subset, right? Sub-object. And you have a morphism here, it means that this guy is less than this guy, right? So then the pullback is this, the pullback of that is that. So then there is a map here, meaning that this is also less than that, right? So therefore, if G and H, like you have here, if G is less than H, then F star G and this guy is F star H. F star G is also less than F star H, right?
Sorry, so this is some general thing about morphisms. You can order them. G is less than H, if and only if G is something composed of H.
Yes.
But this makes good sense only if G and H are not.
Exactly. Because I'm just forgetting the morphism, right? I'm saying that there exists a morphism. So you may say that, okay, but maybe it is important, the morphism. The thing is that if they are monique, then it is unique. If there exists any, so then we don't care. Yes, exactly. And the moniques, 2x is just a sub x, right? So there is an order, and of course the order is reflexive because you can use identity here. It is transitive because you can compose, but not necessarily antisymmetric, but you don't care. So you can just quotient over that. So, okay, so I use this guy to show that pulling back is an order preserving map, right, between sub-objects. Okay. So then before going any further, I have to say something.
Is this
Sure.
order the same as the minimality of the limits?
No, that, that's just an order. It's not canonical order by some universality, right? You have two things. Sometimes you have just two subsets, right? Sometimes this guy is just a subset of the other. Sometimes it's not.
Subset to be subject to monic.
Yes, monic too. Yes. Sure.
So to prove this, you kind of used the triangle pullback thing, right? Or not?
I didn't use the pullback thing. The only thing that I used is that if you have two pullbacks and one map in the triangle. Okay, what do you mean by the triangle thing? The pullback of a triangle is a triangle, right?
Two colored upper left thing. That's part of the proof of the pulling back gives you an order preserving map between the subobjects.
Yes.
And
but the point that I really used is this, that if you have a pullback square here and a pullback square here, right? So this blue one is a pullback. This guy is a pullback. There is a map here.
where is X and Y in
That's good here. So this guy X, this is Y. These two guys are two subsets, right? Two sub-objects. One sub-object, the other sub-object. They are ordered. So this is F star of it, sub-object of X. F star of this guy is a sub-object of X. And then the fact that you can feel this means that if you have this, then you have that. Okay? Sure. Okay, so then the other thing about the pullback. So what should I say? Last time I promised that today we complete the definition of a topos, right? So I said that the topos is a category such that you have all the finite limits, and you can add if you want all finite co-limits, but it's not necessarily a requirement. So plus two other best solutions for some problems, right? Like the limits, co-limits thing that we saw. But before going there, I wanted to say something about pullbacks to complete the story of the pullbacks, and also actually something else. And that something else is that how many, so what kind of logical thing that you learn from the limits, right? Let's say that C is a category with all finite limits, right? And nothing else. This is the only structure that I have. No co-limit even, right? Just finite limits. So what I want to say is that actually it is possible to interpret some parts of first order fragment, first order language inside this guy, right? Because this is our last goal. We want to have toposes, some examples of toposes, this one, that one, right? And then the last thing is that we want to interpret first order language inside the topos, and then use the topos as a model to prove independence of something, right? Therefore, we have to know how to interpret language inside a category, specifically a topos. And of course, whenever you have more structure in your category, you can interpret more things, right? So what I want to say is that if you have just finite limits, then you can interpret a very small fragment, but useful, of first order. You cannot interpret quantifiers. You cannot interpret disjunction. You cannot interpret implication or negation. So then what? So you can implement this fragment of first order, of course, without quantifiers, and then with equality, right? So what I mean is that you have some terms, and then you have this guy and some R of t, if you like. And so these are the atomic formulas that you have. And then you can use just conjunction between formulas and top as a formula. And also maybe it's good to mention that maybe you can have just the zero array things if you like. So as we call it, just atoms, right? Propositions. And that's it. This is the only thing you can do. Okay, you may say that, come on, that's just, but it is not that stupid, right? So think of the axiomatization of groups, for instance. They are just equalities, right? So these are the axioms for groups, right? So you say that, so you have some functions, the function, the constant e. So you have the constant e, and then times between two things, and then the inverse. And then the axioms are just some equalities, like x times e equals to e times x equals to x, or x times x minus 1, x minus 1 times x equals to e, or x, y, z is just x, y, z, right? These are just equalities between terms. So you can describe a...
They're not universally quantified?
It is hidden. Yes. So, okay, let's say that I'm allowed to understand, to interpret any formula in this language, and then we see what it means to have the free x's. But right? Or rings, or any algebraic thing. So that's kind of not very restrictive. So, but at the same time, you have just finite limits. So, right? How to do that? This is what I want to do. How to do that? Let me ask. Let's say that I have in this language some formula A of, say, x1 up to xn. And I want to interpret this guy inside C, the category with finite limits, right? Think of C as your category of sets. And then when you have the category of sets, how you interpret a formula. This is just the usual model theory. How to find a group, say, if you are not really into logic. First, you need a domain. You pick a set. So here you need an object, say M. Right? You fix your object first. Because it is just one sorted. So if you have so many sorts, then so many objects. But 1, 2. What happens then to function symbols? They are just morphisms. And if you have, binary function, then it is just a map on M times M. Because you have finite limit, you have product, right? So you can interpret then your function symbols, say it is an n-array function. So you interpret it as a morphism, right? And what about constants? So this constant, for instance, would be just a map from 1 to M. You have 1 because you have all finite limits. Okay? Fair enough. So then what happens to the relations? What's the relation in set models? It's a subset of that. So if T is just n many terms, right? Let's say that it is just R of x1 up to xn, right? So then what is it? It should be a subset of m to the n. So now it should be a subobject, right? So a subobject, so R, so the interpretation of R, if you like, is simply a subobject, right? So I don't know how to write it. So it is just a subobject of M to N, right?
It's some object and monic map from that object.
Exactly. So the information is more than just, there is one object and one monic, but say up to isomorphism. So, okay. Oh, yes. Yes. So what is it is just a map, a monic map to M to the N, right? From something, say, I don't know, X, whatever. But the point is that it's not really important, but it would be useful if we consider these guys up to isomorphism, meaning that if I have another Y, right, monique, and if I have one isomorphism in between, such that everything commutes, then I pretend that they are the same thing. But that's not really important. So if you do that, then you have a poset of subobjects. If you don't, you have just a pre-order. Right? So, but as you wish. So, okay, fair enough. Now, I have a very good question. Maybe, okay, what about this guy? What is the interpretation of this guy? Equalizer of who? From? No.
From
M squared, because you have two variables. You have M times M. You need a subobject of this guy, right? The interpretation, whatever it is, it should be a subobject of M squared, right?
I mean, I have to say, yeah. Oh, that's it. You're just writing it as a relation.
Yes. Yes. It's binary relation. So then equality, it's just some basic relation. It should be a subobject of M squared. So what subobject? So then we have the to think that, okay, P0 and P1, the projections goes to M. You want to equalize these two guys. So then the equalizer is always a monique, right? So say, I don't know, whatever, and that is just the interpretation of equality, right? That is whatever. You don't like it, huh? No. Is it good enough?
Where is the equality?
The interpretation of equality is this subobject. It should be a subobject of M squared, right? So, yes. It depends, right? So it should be, if you have n many, it should be a subobject of M to the n, but it should be a subobject, yes. And our interpretation is just the set of all things that A is true, right? Okay, fair enough. So then we have terms. So what about this guy? What about R of T? Because we set this guy as a subobject, right, of Mn. And so if you know in the usual first order, if you know the interpretation of this guy, then you know the interpretation of RT1 up to Tn, right? So you first interpret the relations, and then if you substitute the relation with terms, you know how to do it, right? So for instance, here, equality, we know it, but then what happens to T equals to S for two terms, Ts? Pull back, because it is substitution, right? What does it mean? It means that, let's say, that I have R, X, Y, for instance, right? And then I also have T of Z, and I want to put these two guys here to have this RTZ, SC, okay? So I have the interpretation of these two guys and also of these two guys. So the interpretations are, maybe I have to be here. So the interpretations are what? They are these things. One. So what is R? The interpretation of R is a subobject. Say from something, say from, I don't know what. Um, let's say that from Rm, maybe, with abuse of notation, right? So you have this guy, right? And here it is M squared because you have two variables. That's the interpretation of R. The interpretation of these two guys, they should be just maps from M to M, right? So then the interpretation of T is a map from M to M, the same also for S. Now the question is that what is the substitution, right? And it should be just a pullback, right? Which pullback? This guy. This is M squared. This is Rm, right? This is my subset of R. So then what should I put here to pull it back? But you have to substitute T and S. Yeah, no, you cannot. You can, but it is better to do it just once. There, yes. So from M to M squared, right? There is a map. Because you have a map from M to M, one from M to M, and then it induces a map from M to the product by the definition of the product, right? So simply, where are you? So that's this guy. So if you have A, if you have B, if you have some, say, so this is just A times B. If you have some C, one map to A, one map to B, then universality says that there's a unique map here, right? So always you can induce a map to the product. So that is the guy. And I want to write it like this. Say S, now T and S. Right? And then pull it back. This would be just RM, I don't know, of composed with T and S, whatever. Eh? And you can do the same with this guy, right? So there's no difference. It is just a sub-object of M squared, just pull it back over the pair Ts. So now I have the power to interpret any basic formula, right? Meaning that some atomic formulas as sub-objects. And maybe also I have to say that everything depends on the number of variables that you have, right? So here I don't have any variable. So then this guy should be a sub-object of 1, right? So these guys, the propositional guys are always sub-objects of 1, right? Okay. Now, what happens to these two guys? How to interpret them? True, that's true. But then it's, yes, that's true, but there is a point. The point is that sometimes we don't write the variables, but we mean more. So what do I mean by that? So let's say that I have some formula, say R of X, right? And then S of Y, right? When I have this guy, it is a subobject of M. When I have this guy, it is also a subobject of M. But then sometimes you have a conjunction of them, and then suddenly both of them are subobjects of M squared. Here Y is dummy variable. Here X is a dummy variable, right? You need them to just merge, right? So we do it in first order kind of dynamic. We know that whenever you have something new, then you can just expand the set of variables. That is a dangerous thing here, simply because it is possible that we have some sort of MTM. That's not the usual thing in model theory, right? But here it is possible that you have some bad M's, say just MT in sets, for instance, right? That if you do the dummy thing, you kill the whole information. So let me explain. So first, if I have this is of course a sub-object of M, but you can pretend that it is a sub-object of M squared. How? Pull back again. It's right? So how? So like this. So you have now I can move. So let's say that you have R of X. You have R of X. And then we know that it should be just say a subobject of M, right? But then I want to interpret this guy as R of X and Y with dummy Y. How to do that? You say that, okay, so from M squared to M, we have the projection, and you have this guy here, just pull it back, right? You simply pretend that it is here, okay? So I can always do this with adding more variables, right? But say if, it's kind of crazy. Okay, just believe me for now, that how to, okay, I won't explain it for now, but let me just put it in this way, that if you have a formula, we said that it is a subobject of something, right? So this guy is a subject of M, or M squared, or M third, or what? That's kind of ambiguous, right? There is a minimal version, But that's not a very well-behaved thing, because then when you want to work with another one, you have to expand it, right? So to solve this issue, there is a way to do that. The way is that they usually write the context. So when they say that we interpret R, they say that actually R, say, there are different ways to write that. So say R, for now, in context X, right? Or it can be a context XY, right? The context, of course, is bigger than the variables that really you use, right? And then the whole information tells you that R should be a subset of M squared or M or whatever. And then what we observed here, the dummy thing, simply says that if something is in the context of some variables, you can just add another variable in a dummy way, right? So then, now what happens to top? I want to ask again. It depends on the context. Top has no variable, of course. Therefore, it is just the obvious map from 1 to 1. But maybe we can interpret it in bigger contexts, right? So say top in context x1 up to xn. What it should be? It is there. Exactly, but it is the identity, exactly, right? It is just mn to mn, the whole thing. And then the last thing is just that that guy, this conjunction. So, okay, first let's make everything in one context, right? So I assume that I have R and S both in context x1 up to xn, and then I want to construct R conjunction S. If it is not, then you can expand your context, right? So what is this? These two guys are sub-objects of M to the N, right? What is this? What's the intersection? Pullback, okay. Right? Because think about that. So this is your R. Say this is your S. This is your R. Right? The pullback is the best guy that you can put here to fill the corner. And it is, of course, the intersection, right? So then why not the pullback? So it is. Right? So I have pullback, I have one, I have product, I have all finite limits, and therefore I can do all these things in my category. To interpret any formula in this very restricted language, right? So
every formula in context becomes a sub-object.
exactly. Then we come back to that universal thing that Neil mentioned. We don't have universal quantifier, of course, but we have a way to say that this guy, so we have a way to say that R of X is true, always. How to do this? Let's say that you have a language, you write some formula A of, say, A in context x1 up to xn, right? And then we have the category C, and then we can interpret A as, say, AM, sub-object of M to the N, right? And now I want to say that actually A holds all the time for every X. I can say that, right? The categorical term. Simply I have to say that what? Yeah, that's just two set theoretical, yes. So I have to say that it is isomorphism or it is isomorphic to M and to Mn, right? This is just the total subobject. You can write it, right? simply say that this monic is isomorphism, right? Because this guy is just all the instances of A in M to the N, and A holds for everything simply when it is just the total, right? It is everything. Okay. So actually, I have a bit more power than that. And there is no. So a map is isomorphism if it has an inverse, which is kind of weird, I know.
Well, I'm just wondering what this means for an interpretation. So you have your language and you choose your interpretation by choosing which arrows correspond to which symbol. Then you may or may not have if you have a function, morphism going back the other way.
Yes.
So you can make it.
Okay.
So you can't just add a new arrow because that'll mess up.
Yeah, of course. The category is there, so you cannot add anything, right?
So you can interpret, you can look at the category to see where the arrows are, and that tells you whether it's universally true.
Exactly. So, what I want to say is that actually we can say more than A is always true. It can have some sort of one layer of universal quantifier here hidden. We can also have one layer of implication, but not more, and also together. So what does it mean? It means that if I have A and B in some context x1 up to xn, this is the way to write it down, right? This means that the interpretation is that whenever A is true, B is also true. For any x1 up to xn, A is true, then B is true, right? So therefore, you can read the first guy as top A, right? So you can interpret it like what? Because this guy is a subobject, right? It is this guy. And that guy is also subobject, right? So of course, that relation would be just the order between subobjects, right? So I'm simply saying that A is less than B, meaning that there is a map here. Or these two guys as subobjects of M to the N, they are ordered in obvious way, right? So these guys, I can interpret. So if your A and B are in this very restricted fragment, then I can interpret this in any category with finite limit. And it is reasonable. What does it mean? It means that, of course, I can come up with any, weird interpretation. Who cares? The point is that we chose the interpretation in the right way, and how to see it formally. It means that whenever you prove really in a natural sense via these kind of sequence, then if they are true, the consequence is also true. What does it mean? It means I don't want to write all the rules, but say A always proves A. So let's just forget about context for now. A always proves A. That's true, always. Simply, I'm saying that, the order is reflexive. Or A, B, B, C, you get A, C. Of course, the subobject order is transitive. Or more. So always A proves stop, of course, because this is just the biggest possible subobject, right? This is the top. The other one. Let's say something about the conjunction. So if you have A, B, and A, C, you have A, B, and C. How do I know that? By the definition of the pullback, right? So if you interpret this guy, it would be m to the n, say a, and this says that b, right? Okay, so that's not good. Let me be reasonable. So m to the n, this is b, this is c, right? So, and this is just a conjunction, right? By definition, this guy is a pullback square, right? So what I'm saying is that A is less than B, and A is less than C. Then pullback says that A is less than. So I defined in a natural way everything, and therefore my notion of satisfaction, say, respects the usual logical rules. Okay. So, okay. Then let's say something about the groups. So because groups have the axioms in the obvious bracket, right? So what if I want to have a model of all the axioms? Where are you? So all the axioms. So meaning that this would be, so I have to come up with some object M and some maps in obvious way from M to M, from 1 to M, from whatever. And then such that the sub-object defining this guy is the whole, and also the subject defining this guy. And the same here, there, right? So to satisfy all the axioms. So that guy, in for very obvious reasons, if I have C with finite limits, then if I have some object M, of course, with more data, right? So say a map, this E is a map from 1 to M, some dot as a map from M squared to M, as with some inverse as a map from M to M, right? So if this data satisfies all the axioms, then I call this guy a group object for obvious reasons, right? Inside C. So for instance, if my C is the category of all topological spaces, then the group object would be topological. If my C is this guy, the variable sets that we had before, what would be the group object? Two groups and a homomorphism. And what? Okay, you get the idea. So that's the thing. You can interpret inside different categories that kind of language if you have finite limits, right? So later, very, very later on, we see that if I add more structure, say finite colimit, say, I don't know, the other topos structure or whatever, right? So then you get more power to interpret more language. You can interpret disjunction, you can interpret implication, quantifiers, higher order quantifiers, right? More than that, very basic. But the idea is just the same, right? Okay, so that's good. Of course.
Well, say groups, right? So I can imagine the simplest interpretation of something like X equals EX. Just that you have two morphisms and just say those two morphisms are actually equal. Right? Yes. Yes. But officially, I guess you're doing something different, right? Because you're saying
yes, and they are the same.
But they are the same.
They are the same. They are the same. So the thing is that if I have just pure algebraic in the sense that I have just some functions and one equality, I can do something easier just to with say one and product, without the equalizer thing, because I can just simply work with the maps, right? So you can say, so I can reinterpret the thing like that. What should be the group object in a category? Just forget about all these things. It should be something with the isomorphisms, such that what? Such that the composition, for instance, of this guy and then the inverse is just E, okay? In an obvious way. Because you can just work with equation between equalities. So you can have that. But if I have some conjunction of things, then it is just external, right? I want to make it internal. Okay. And of course, if you have more like quantifiers or then that doesn't work. So yeah, of course, always you can interpret in obvious space. Say if I have for all x, then you can say that okay, read for all x as all the maps from 1 to m, right? That is not usually enough because as we saw, it is impossible for some categories to all the points are not enough to capture m, right? But you can say the same thing kind of with generalized elements, like from something to m, some x to m, and it somehow works with some care. This is one of the things that we have to see, because of course, you're working with sub-objects in some category could be just tedious, right? So because you don't know how to compute, you have to really compute equalizers of something and then pullback of something. So always we want to have the handle, right? To say that, okay, this is the natural way to interpret it. This is equal to the theory, but this is the way to compute things. And this is the main idea behind the forcing kind of argument, right? The forcing argument simply says, in this new language, that you have some sort of weird category, and then in that weird category, you interpret the axiom of choice, and this is false. But then the problem is that interpretation is in this sense, right? And you have to add quantifiers and other things, right? And it is just a mess to compute everything. But then there is a way to compute it. That way is via the underlying poset. That's the usual way that people define it, right? So that is, in our setting, it's called the Kripke-Joyal semantics. So we will see that, hopefully. Okay, so that's this part. I'm not sure if I have to go further or not. Okay, why not? So, because that's not that hard. So I have to feel one of the things that I promised, because that's not that hard to explain. So, so we had the definition of toposes, right? So a topos is a category with all finite limits and two other things, right? And one of the other things is what? Do you know that? Cartesian, yes, so the exponential. So you remember the idea, right? So we look into sets, the category of sets. There are some structures, seems random. Then I pick some, write it in the categorical language, and then put it as axiom here, right? So we had the finite limits, product, blah, blah. And then another one that I want is just a set of all functions. That's the thing that we have in set theory. If you have two sets, right, set x and set y, then there is a set of all functions from x to y, right? The question is that how to characterize this guy in a categorical language such that I can use it as axiom here. Hmm? Any idea? That's a bit weird one, but not that much. It should be universal in some sense, right? It should be the best of some with some property. Okay, let's make it easier. So first, this set, whatever it is, it should have some relations with x and y, right? What is the relation between this guy and x and y? So let's call this guy y to the x, right? And then what is the relationship between these things? Yes, but okay, so it's determined, but one way of it is what? So whenever I have a function and I have something from x, I can apply it and get something in y. That is the obvious relation that they have, right? So then there is a function, actually, the evaluation function, right? So the definition of this guy in the categorical language is this. This is the best possible solution for this thing. Meaning that one, you have a morphism like this. Two, for any other guy, say C or Z, such and any other morphism, F, this guy is the biggest. Meaning that there is a unique map such that, let's say that G, the unique G such that G times identity makes this guy commutative. So the first part says that these guys, whatever they are, you can use them in applications, and you have all of them and nothing else. Right? This is just the biggest. It is sort of universality, right? Because it is just the best solution of something. The best point that fills this gap, right? So it is the best guy that fills this empty, right? In some form of sense. So, and of course it is unique, blah, blah, but the guy is, it's not a limit in the obvious category C that we have, but you can make it a limit in another category. But it is just the best solution to something. Okay, good enough. So then I have to make some examples of this, right? So of course, the obvious example is just the exponential, but the other example is in posets. In a poset, the exponential would be what? Let's say that I have a poset. Yes, I did, but it depends on how formal you want. So, but I can do that. So I can repeat y. Why not? So you have x, you have y. What is the exponentiation y to the x object? It is, again, not just one object with some morphism. So it is the object, let's call it, I don't know. So let's A and B, and then the C with the map like this, the pair C and this map is called the exponentiation of B to A, say. When for any other such map,
Whole picture, the expansion.
yes, C together with this map is exponentiation. When for any other guy like this, fixing A, B, changing B, there exists a unique map from D to C. So for any F, there exists a unique map G, such that G times identity of A makes this commutative. So note that I'm saying that this guy is unique, not this guy. So the filler here is not unique necessarily. So this guy is unique, right? right? So that's the definition. So now, yes, because it's meant to be something like this, and this is just the usual notation. It's a pictorial notation to say that this guy is unique with the property.
But you didn't use it before.
I sometimes have my bigly thing, right?
Okay.
So what happens in a post? Let's say that I'm in a post and I have two objects. But then the post-it is P and the order, the objects are A, B in P, right?
So that's your category.
Yes. And then I have two objects. And what would be the exponentiation? So it is some node, C, some element, together with the morphism like this. And the point is that in post-it, we have just one morphism. So what I'm saying simply is that C meet A is less than B, right? So it is a C, but not any C, a C such that CA is less than B. And this is the best C, meaning that 1, 2, for any D, if D meets A less than B, then D is less than C. You don't need any uniqueness or commutativity, right? Because it's just a post. So you know this guy, right? It is just now really the greatest solution to this guy, right? And it's called the Hoiting implication, right? Equivalently, you can describe it like this, that C, usually denoted with this, simply you have this. So these guys mean this, but then it is possible, and the other one, but it is also possible to describe it like this, that D is less than A implies B if DA is less than B. So these are the usual introduction elimination rules for implication, if you know it, right? So this guy, exponentiation in a post-it has a name. It's called the Hoiting implication, and it's used to interpret the implication in logic, right? So, for instance, if you have this post-it, so let's say that X is a topological space, O of X is just the post-it of all opens, right? This post-it has all finite limits and co-limits because you have, the intersection, finite union of any open is open. But you also have this guy, the Hoiting implication. So because if I have U and V, two opens, and you define this guy as, this is just the usual implication, right? Either U is not true or V is true, but this is not open necessarily, so the interior of it. If you check, then you see that you have this property, really. So any topological space provides a poset with Hoiting implication, right? So you have exponentiations, okay? So what I want to say, just as the last thing, and we will continue. Okay, do we? Okay, so let me just close up with this thing. And then we will see more about the exponentiation next time. Specifically, what happens to exponentiation in the category of G sets and variable sets or whatever, and they are not then pointwise. It is not an obvious thing for the first time. But the closing thing would be that what is a Cartesian closed category? CCC, they're called. So Cartesian closed category is simply a category with all finite limits. And all exponentiations. Right? So this is the second guy that we had.
That means this picture of every A and B.
For every A and B, there is C endomorphism such that blah, blah, right? So a poset with which is a CCC poset, usually is not that interesting, but people are also interested in this guy with all finite co-limits, right? So simply you are saying that I have all the joins, all the mates, finite ones, and then implication, the Heyting implication. And this guy is called Heyting algebra. And the best example of Heyting algebra is just these guys. So if X is a topological space, then always O of X and the order is a Heyting algebra, right? And people use this as the model of intuitionistic logic, right? Because as you can see, you can kind of interpret the full, okay, not the full language, the full first order, but at least you can interpret disjunction, not just conjunction and one. You can also interpret disjunction and implication, sort of, right? Here. So these guys are called the Heyting algebras. Next time, I will explain why I will start with something that these Heyting algebras, how they are, of course, related to topology, but at the same time, they are related to logic because they can be models of intuitionistic logic. And then I explain, without any definition of topos yet, that a topos is the higher order version of this guy. A topos is a higher order version of Heyting algebra. And therefore, it is obvious that it is kind of related to topological spaces. It is the generalized topological space, if you like. And at the same time, it is a generalized model for intuitionistic mathematics. We will see that next time. Yes, thanks.
I guess this is a chance for the online people to ask any questions.
Okay. Yes.
So here in this category C, you have finite limit, but actually, like, we use only some particular types. Like you used only pullbacks, products. But
yeah,
they're enough to construct all the other.
Yes. Because of course we need pullbacks, right? That's obvious. Also, we need one for the constants, and that's enough to construct all the finite limits. So, sure.
So here CCC poset means Cartesian closed category,
Which is also a poset.
and not has not have anything to do with California.
I know. Sure.
So here you
Yeah.
said, yes, you said like how to interpret predicates and like this fragment of first order logic in a category.
That's true.
But if you look at just this propositional fragment, that it would get much simpler, right? It would have just like that conjunctions are products and maybe that's it. And
it gets simpler, but if
like this object
yes, if we want to follow the same kind of line here, then you need one. This is your object, right? Your M should be one because it's propositional. Everything is a subset of one. So you need just one, sub-objects of one. That's good. And then you need your sub one to be just a meet semilattice at least, right? You have all the structure, but you don't have the meet necessarily. right? And yes, but not in the main category, in the sub-object category. Sub-object is a post-it, right?
Yeah.
Their meat is the product, but if you go, into the main category, it is a pullback.
But pullback with the terminal object as a target, so that it's still just like the same thing as product, no?
Is it? Yes.
You can just ignore the one.
Yeah, that makes sense. Yeah, you're right. You're right. You're right. You're right. You're right. Yes. So then product is enough. That's true.
In this simplified sense, like this I think implication.
Yes.
It's like just a proposition thing. Like
True.
Your objects, here you can just do that objects are propositions. Right? Product is the conjunction, and this, I think, this exponentiation would be the
implication. Yes.
Like this external equivalence would be just isomorphism between objects, right? If you won't say that the propositions are.
Yes, because there's just one morphism to one, so you don't care about the triangle, then it simply means, yes, the existence of isomorphism. That's true.
Ilario, did you have a question?
No, at the moment, no. Everything is fine, thanks.
Let me pause this guy or no? Actually, no.